Here we have a completely pointless video. Probably. I'm not even playing music from Lord of the Rings Online in the background to make it amusing. Current page, derivation of that famous 8-inch formula. Yeah. For any arbitrary circle at first, if we just look at the this bit of text here and ignore the rest of it for a while. For this arbitrary white circle on the left, with its centre just on the screen where the blue and orange lines meet, you have this blue vertical line. I'm off to a good start today. To a position at the top of the circle. You have a purple horizontal line crossing it there, tangent to the circle, sticking off infinite distance both ways, but I've only drawn part of it. You have an orange radius, well, an extended radius, a radius continued, whatever term you want to use, from the centre out through another point on the circumference, and probably have to click for the mouse to show up, and maybe even be slightly zoomed in and click for the mouse to show up. From the centre down here, where there's an angle A marked between them, to the top there, you have this pale blue vertical line. You have this orange radius extended beyond the circumference out here, passing through that point. You have a purple tangent to the circle at this point. And I have drawn an additional line in lime green, linking the 2 points where the vertical and that other radius, 2 radii, cross the circumference, marked C. So we have X, your horizontal displacement, Y, your vertical displacement, and C, the chord length. Mathematicians, people who stayed in school longer than Mark Steele, may recognise this as a right-angled triangle. There's a little right angle marked up there in the top right. I've also marked right angles there and there. The thing about right-angled triangles, you can very obviously copy that triangle, rotate it 180 degrees and put it underneath C to make a rectangle. Still length X, still height Y. You now have this point way beneath your feet, which is, well, isn't really a good way to describe it, but from which a line parallel to your horizontal, this purple tangent up here, goes through the circumference at the same point as that other radius, the orange one, down there. Strange description, I know. By Pythagoras Theorem, we have this top line, x squared equals y squared plus c squared. That's, the square on the hypotenuse is equal to the sum of the squares on the other two sides. You didn't even have to pass the 11 plus exam to remember that much. Rearrange that, x squared is c squared minus y squared. We can express this horizontal distance x, horizontal from you to a point in space, x squared, as being the difference between the square on the chord length and the square of the vertical displacement, this y displacement. We can also look at this larger right-angled triangle that we've created here, between centre of the Earth and that buried point and the other point on the circumference, and say that this side that is most of the radius, just minus that little bit, that drop, r minus y, all squared, r minus y all squared, plus x squared, the same x squared, it's this x here rather than this x here, but it's still the same x, equals r squared, because the hypotenuse of that triangle is the radius, the orange one here. Expand r minus y all squared, r minus y times r minus y, plus r times plus r is r squared, plus r times minus y is minus ry, minus y times plus r is minus ry, so it's I plus r squared minus 2ry, minus y times minus y is plus y squared, r squared minus 12y plus y squared. X squared, we already know to be c squared minus y squared, so we can replace that x squared with c squared minus y squared, and we get r squared minus 2ry plus y squared plus c squared minus y squared equals r squared. We have a plus y squared and a minus y squared in the same side of the equation. We can just get rid of those. And we have plus r squared on both sides, so we can subtract r squared from both sides, and we're left with minus 2ry plus c squared equals 0. Which sounds better if you say it's c squared minus 2ry equals 0, which is another way of saying c squared equals 2ry. And we can rearrange c squared equals 2ry to say that y equals c squared over 2r. This is a generic formula for any circle where you're drawing this. Excuse me a moment. Man. I said cycling would be good for me. I didn't say I would have itchy little bits of plants stuck into my ankles afterwards. For a circle with a radius of 6,371,000 meters, I should point out that's assuming perfectly circular Earth, and of course the Earth can't be perfectly spherical because it's rotating. So the radius is not that everywhere, it's only that in a few, well, in a couple of sets of places, and the radius of the curvature isn't that everywhere, it's probably that in a couple of other sets of places, in particular directions. But for this hypothetical circle of that radius, y in meters, because we're working in meters, because we're sensible people. I mean, seriously, have you seen, I mean, thwips and barleycorns and inches and yards and furlongs and rods and chains and leagues and rods and roods and acres, and it's daft. And don't even get me started on gills and drams. Y in meters is the chord length in kilometers, because people tend to do distances in kilometers, squared, times a million, because we want it in meters, not kilometers, divided by 12,742,000. Divided by how much? Well, that's twice r, isn't it? 2r from up here. Diameter of the Earth. Well, twice the volumetric mean radius of the Earth. Might be the diameter of the Earth in many, many places, but not everywhere. Or y in centimeters is the chord length in kilometers squared times just 1,000, because you can knock the 3 zeros off the end of that number and off the end of that number. They're top and bottom of the same fraction. Divided by 127.42. Why the decimal point suddenly? Because we're in centimeters. From meters to centimeters, obviously you're multiplying by 100, which is the equivalent of dividing the denominator of your fraction by 100, moving its decimal point 2 places left. So the y, this drop here, is the chord length in kilometers squared times 7.848 centimeters. If you want to work in ancient units related to the top joint of the king's thumb and various other bizarre things, we can go to miles. Y in miles is the chord length in miles squared divided by twice the volumetric mean radius in miles, the diameter of a circle with that radius. In miles, which is 7917.5, if you want it in inches, it's very simple. You take y in miles and multiply it by the number of inches per mile, which is 63,360. That number's coming back later. 63,360 divided by 7,917.5 is 8.0025142. Basically, 8 inches. 1 mile, 8 inches. And because we're squaring, 2 miles will be 32 inches. 3 miles will be 72 inches. Very simple. Illustrative example. Well, actually, more calculations first. A, this angle down here, is the angle whose sine is x over r. The sine being the opposite over the radius. We're still talking about this right angle triangle from this buried point to this other point on the circumference, not all the way up to here and here. Just to there, and just to there, we have x over r as the sine. The arc length from where you are here to your target here is that angle in radians times the radius, because that's how radians work. For a small value of x over r, in this case, as an example, 15 kilometers on a radius of 6,271 kilometers, that arc length and this x horizontal displacement and the chord length c, they're about the same thing. That's what this means. This line here, arc is approximately x is approximately c. For that example, the angle is the arc sine of 15 over 6371, which is 0.00235 radians. The arc length is that times 6371 kilometers, which is 15.000 kilometers, which is x, right? And the chord length is x squared plus that y displacement squared, all square rooted. It's this formula up here. And it works out as 15.0000 kilometers, which is x. You have to go to an awful lot of decimal places to even see the difference, right? It's fifth decimal place, there's a 1, so what? For the larger values, there is a difference. If we take x 4,069, nice. And the same radius of 6,271, the angle is the arc sine of 4,069, nice. Over 6371, which is 0.69, nice. 27754. The arc length is 4,413.7, and the chord length is 4,325.9, and those are very different numbers. But here, we're looking at, for 15 kilometers, which is the kind of distance over which you'd actually bother using this formula, you have 15 kilometers. If you're actually using a laser rangefinder, you'd be somewhere way up here above here where you can actually see that target. More likely you're using a map, which is giving you the arc length. But between 15.0000 kilometers and 15.0000 kilometers and 15 kilometers exactly, the difference is measured in, that's like 10 centimeters, 14 centimeters. If you're using 155mm howitzers and dropping high explosive shells that create instant swimming pools when they come down, that's close enough. Right. So there's your 8 inches formula anyway. If we're talking hidden height, those little errors about arc length and chord length and x displacement and line of sight length don't really matter. Your line of sight length will be half of this purple line. What does really matter is, of course, you have observer height. You may not be able to see that yet. Your line of sight length would be the purple line, not the shorter chord line between where orange and white intersect underneath, and not the longer, I think it's longer, intermediate length of this white arc. It would be the purple line of sight. But again, on a thing the size of the Earth, over the kind of distances we would use this, the difference isn't much. What does matter is that your observer height has to be taken into account. When someone says, look, I can see the tops of these buildings in Chicago, and never mentions not being able to see the bottoms of these buildings in Chicago, from all this distance away, when according to 8 inches per mile squared, which is not how that formula should be expressed, they should be hidden behind this much drop. They've quite often failed to mention that they were 400 feet up a sand dune. You've got to calculate this. You've got to reverse the formula and calculate this left side of the near side of the purple line, your line of sight, and subtract that, or calculate the arc along here, or this chord length from here from sea level below you to sea level at the horizon. But again, they're nearly the same thing. And subtract that from the distance, and then work out how much the remaining distance means should be hidden. And it's not even that simple, because refraction. Which means your line of sight is going to look like that instead. Not necessarily to scale. I mean, obviously not to scale, because if you were this high up to scale, you'd be way out in space, and this part of your line of sight up to here wouldn't be refracted. It would be this bit along here that had all the refraction, and then out here there'd be no refraction again. Because Space. But anyway, that's not what prompted this pointless video. This is. Starting on the left, follow this red arrow 1 mile to this vertex here. Probably need to make sure you can see this. Starting here, follow red arrow 1 mile to this vertex here. You drop 8 inches because you've gone 1 mile. Follow this green arrow 1 mile to here. You drop 8 inches because you've gone a mile. Follow this blue arrow 1 mile to here. You drop 8 inches because you've gone a mile. But you've come back to the same place. You're not 24 inches lower. Dun, dun, dun! Paradox! A paradox! A paradox! Actually, Gilbert and Sullivan come up with better paradoxes than this one. Why do I say it's a pointless video? Well, the people who are going to understand it probably already do. And the people who need the explanation are following a guy whose income stream depends on him never publicly understanding it. The guy who came up with this so-called paradox. He does videos about how much he doesn't understand this and asks for money. If he publicly understood this, he'd have to stop asking for money for not understanding this. Now, what any actual surveyor would do, of course, would be set up the surveying station in the middle of the work site, here, and survey everything from the middle of the work site. So we have this central location, and from here you can survey that point, and that point, and that point, and indeed the midpoints of the sides of the triangle. On this diagram you still have the same red arrows. From the top we have the red arrow down here to the bottom right, we have the green arrow across to the bottom left, we have the blue arrow back to the top. And you can see on this diagram, from point A where you start, point B is over here, point C is over here, and they're equidistant from point A. And this midpoint of side BC is a little bit closer. So, as seen from point A, side BC is up just a little to the midpoint and down just a little to C. As seen from point B, side CA is up just a little to the midpoint and down just a little to point A. As seen from side C, side AB is from 2 inches down, up just a little to the midpoint, and then back to 2 inches down at point B. So, there you go, there's your answer. But we're going to do it properly and survey from the centre. Yes, I've marked on 0.57735. Assuming the sides are 1 mile, each of these distances from centre to a vertex is 0.57735 miles. If the sides are 1 inch, each of those distances is 0.57735 inches. If the sides are 1 rod, each of those sides is 0.5735 rods. If the sides are 1 chain, there are an awful lot of units we could use. The maths work out exactly the same way, whichever unit you use, as long as it's a unit of length. If you find yourself using units of seconds or litres and doing calculations like this, something has probably gone wrong. Or you have gone way beyond any physics I ever studied, because you got some funky dimensions going on. But anyway, I'm going to survey from the centre. And I'm going to convert from miles to inches, so we get that line from point A out here on the right to points B and C on the left, 36,580.9 inches to the right and 18,290.5 inches left. And there's our 2.6675 inch drop, because that triangle would be down here. And you can see there is a little bit of white above our purple line on this left side, because of course points B and C are down here at the left end of the purple line, but the midpoint of point BC is above it. Oh yeah, there's that curved side. And in fact this purple line is a line from point to point. The side AB would be up to the level of the white surface here under the left hand orange arrow, somewhere about where the decimal point in the 36,000 figure is on the right. So we have a curved red arrow over the surface, which I haven't drawn in. We're still in inches. Why are we still in inches? What am I? Boomer? No. I was not born in the 1940s. I'm going to convert to millimetres. Move up to the top left. We're going to have our radius is now 6,371,000,000 millimetres if you're European, or 6,371,000,000 if you're a Yank. Millimetres radius, and we're still on a perfect sphere, not on the distinctly oblate and kind of bumpy Earth. We're going to put our survey station in a very obvious place. Well, we're actually going to put our survey station in the middle of the site, but we are going to designate our survey station's location with the very obvious choice of coordinates 0, 0, 637100000, which means our frame of reference is centred a heck of a long way directly below our survey station. But we're measuring everything from the survey station, which is what you do in the middle of the site. Because we're not stupid and we're not scared of negative numbers. Vertex A is now at, how many thousand inches that was, 0.577 something miles, right? To the right, which is 929,155.192 millimetres. Most of a kilometre. How convenient. In the positive x direction. 0 in the y direction, because we have lined up our x-axis with survey point, vertex A, because that simplifies things. If you've got to point it somewhere, you might as well point it somewhere you're going. And 63709999932, which to most people will be 637100000, but it's not quite. Then we have triangle vertex B. Now triangle vertex B is not as far in the negative x direction as vertex A was in the positive x direction. Go back to the equilateral triangle. Vertex B is in the bottom right. It is not as far down on your screen from the centre as vertex A at the top is up from the centre. But it is out to the right. It's not as far out to the right as the full width. It's half a triangle length out to the right. And half a triangle length is 0.5, not 0.57735. So you'd expect this number, this y coordinate of vertex B, to be slightly less than the x coordinate of vertex A. What do we actually get? We get 800,000 rather than 900,000. So yes, slightly less. Negative, because B is in the negative y direction. And we have the same z coordinate, the same distance from the centre of the Earth in the direction that is up, directly up at the survey station in the centre of the worksite, where a professional surveyor would put it. Triangle vertex C, this is an equilateral triangle, so this is very, very easy to do. It's the exact same as vertex B, just with a positive y coordinate rather than a negative one. Wasn't that easy? Vector AB is now from plus 900 and some thousand to minus plus 930,000 to minus 465,000, which is minus 140,000. And from 0 to minus 800,000, which is minus 800,000. And 0 is going from 637099932 to 63709999932. There is 0 change in the z coordinate. There's no drop. Vector BC, you're not moving in the x direction. On the equilateral triangle, the line across the bottom of it was horizontal on the screen. There's no change in this coordinate from B to C, so it's 0 there. But you are going from negative 800,000 to positive 800,000, so that's plus 1.6 million. And again, there is no change in the z coordinate, so again 0, no drop. Vector BC, you're going back from the bottom of the triangle to the top point in that previous diagram. So where we had minus 1393733, we now have plus 1393733. And you've got to subtract the other half of that 1.6 million to get back to 0. That 0 y coordinate of point A. And it's still 0 change in the z direction. It's still the same z coordinate. There is still no drop. So that minus 1.4 million plus 1.4 million equals 0. Well, plus 0 equals 0. Minus 800,000 plus 1.6 million minus 800,000 equals 0. And plus 0 plus 0 plus 0 equals 0. You are indeed back where you started. So where did all the drop go? Because there were 3 1-mile sides, each of which has an 8-inch drop. Where's the drop? There is no drop. As surveyed from the survey station in the centre of the work site, like a professional, there is indeed no drop from point vertex to vertex around that triangle. And, obviously, it's a triangle on a surface. No matter how bumpy and chunky that surface is and how many weird features you include, if you walk all the way around the path back to where you started, you're back at the elevation at which you started, so there is no drop. But there's drop in the 8-inch formula. Where did it go? As I'm sure we all know, or are going to pretend not to understand because our income streams depend on us pretending not to understand it in some cases, vertical at vertex A isn't 0, 0, 1. Vertical at the survey station is 0, 0, 1, or 0, 0, minus 1, or 0, 0, x. Sorry, bad choice of variable. 0, 0, n. 0, 0, any value is vertical. It's a vertical vector of some length, that value, right? At vertex A, that's not vertical. That's parallel to vertical at the survey station. At vertex A, vertical is the sine of the angle that is 0.577 miles, well, it's 929 meters over 6,371 kilometers, which is 0.000146, 0. And the cosine of that angle, 930 meters over 6,371,000 meters, which is 0.9999999, which is really damn close to 1, but it's not 1. It's really close, but it's not 1. Just like, 8 inches is really close to being 0 miles, but it's not actually 0. In that frame of reference, if you use a frame of reference that's aligned to vertical at point A, not to vertical at the survey station, oops, this vector for side AB that was minus 1,393,732.787428, that x component of the vector changes to minus 1,393,732.772606. Very slight change. In fact, it's 0.9999999 of that. Your 804672 remains the same because you're only rotating around you're rotating around the y-axis, so your y component of the vector doesn't change. Your 0 goes to minus 203.263860 millimeters. 203 millimeters. What's that in inches? Well, that whole vector in inches, minus 54,870 some, minus 31,700, minus 8. There's your 8 inches. By Pythagoras' theorem, we can combine this 54,870 and 31,700, and we get 63,259.9995, also known as 63,360 inches. Told you that number would come back up. It's a mile. Of course it's a mile, it's a 1-mile triangle. 1 mile away, 8 inches down. There's the drop, exactly as expected. See, when I started, I was describing the blue line as vertical and the purple line as horizontal. And they are, from the point of view of an observer where the blue line intersects the surface. From that observer's point of view, the green line is a vertical drop to where this other radius, in orange, intersects the surface. Purple x, green y, blue vertical, orange other radius. from an observer here, where this orange other radius intersects the surface, the orange line is vertical, the green is horizontal, the purple is the drop to where this blue other radius intersects the surface. It's the frame of reference. Got to keep track of your frame of reference. And a good man always knows his limitations.